Hello, everybody. Apologies. My name is Travis Chisholm. Getting a phone call. This is the very first video that I'm recording for the upcoming summer 2026 Calculus 1 class. This is, part of what's going to try to help you through some of this material. There's lots of material available in Pearson as well. And then there's also, you don't just have to communicate with me through the videos. Of course, I'm always available by email if you ever want to talk, ever have some conceptions on things, and I'm sure that I can help you out with some things. So I want to start off with section 1.1, which in Pearson is called the review of functions. So just to kind of tell you a little bit about what this class is going to look like, section 1, specifically chapter 1, is going to be what I considered a review of what material do you need to be successful in this course. And a lot of this, hopefully, is coming from a college algebra. If you've already taken and hopefully all of you have taken the hardware check, just making sure that Respondus lockdown browser, everything is working great there. You'll know that you'll see that I already asked this question, and I'm curious to get to know your answers, but I just want to make sure that we're all on the same page on what we're trying to head for. So this is kind of starting our review of functions. So the first question is, what exactly is a function? There is a, MyLab's definition that we'll get into, but I like to think of a function. A function is a rule that connects inputs and outputs. Okay, so what does that exactly mean? We have these input functions, these input values. And let's maybe here we'll have input, and over here we'll have output. You can see there's some things from the inputs. We can use letters, we can use numbers, we can use symbols. And then we have some things in the outputs. And once again, these can be letters, they can be numbers, or they can be symbols. Whoops, that's going to happen a lot in this class. I'm working on the getting my online whiteboard skills better. In case you haven't noticed, it's just a paint program. So what what a function does is it connects members of this input set to members of this output set. Okay? So for this specific function, and maybe we typically will call a function, let's call it f. So in this case, we see that f of a is equal to w. We also see that f of b is equal to w. And that turns out is fine. There is a repetition that we don't like that I'll talk about in just a second. F of 4, looking at my lines, is 3, and then we have f of... Oh, I'm sorry. That should be f of c, and f of b turns out to be omega. Okay? I want to point out, this is what we consider a good function. Okay? It is a rule that connects inputs and outputs. And maybe I should specify, it is a specific rule that connects inputs and outputs. The set of all inputs we call the domain of a function. So what is the domain of this particular f? We have a, b, c, as well as the number 4, all being members of the input. I could say that the domain of this function is specifically the set that contains a, b, c, and 4. Versus the domains we usually refer to as the range. And what do we have? We have w, we have 3, and we have omega. So, the question is, when are these relationships, when are these specific rules, when do they satisfy actually being functions? Okay? And the important thing to note is, what we just have is a function. Notice we have a repetition. Both a and c are getting mapped. I guess this is where I'm going to try my best to make this the normal classroom schedule of whiteboard language, and I guess I should get used to making these sort of eraser mistakes. We notice we have two inputs going to the same output. That is fine. the rule is each, and that's going to happen a lot, input must have at most one output. So, something that would not be allowed to be called a function. Let's go ahead and use our language of domain and range. So now we have this function g. And let's use some similar elements. We'll use a's and b's and c's. And over here we'll use w's and omegas. So a goes to omega. Sorry, I meant w. B goes to w. And it looks like c is going to go to omega and w. This is a problem. Specifically, not a function. You cannot say that g is a function. And the reason for this is because we have one input, f of c, is both omega and f of c is w. We don't want to have that. So the question is, what is the specific relationship that we're going to define as functions? And remember, we can have this type of repetition. A, the input element, only has one output element. Every time you type in A, you get out W. Every time you type in C, you get W. That repetition is fine. The bad repetition is, how are we inputting one input C, yet getting two different outputs? That's the one that we have to avoid. So, let's get a new board. I don't want to say that. Okay, so a couple other questions that we might have when it comes to these functions is, how can we represent them? So the first way, we can have what's sometimes referred to as a list. Okay, so I might say, we're going to call them ordered pairs. And this is something you've seen hopefully a lot in a college algebra class. So let's call a function f. It's going to be the specific input-output. So borrowing the f that we had previously, I think A went to W. I think B went to omega. I think the letter C went to omega, as well as we have 4 going to, and I'll be 100% honest, I don't remember the last symbol that I used. We'll say it's V. Is a function. Now, notice each of these represent an ordered pair that we possess, and it understands the input and the output nature, and we just have a finite list of them. Now, before we continue, I'm going to write a function that is going to be more useful for the other types. So let's say I had a function that had 0 and 0, it had 1 and 2, it had 2 and 4. Let's get some negative numbers. Negative 1 and negative 2. Let's say it also had negative 2 and negative 4. That brings me actually onto the way of my second way that I can represent this with a graph. We're going to put x values down on that. We're going to put y values all the way up here. Okay? And then we can graph these. Let's call it 1 and 2, 1 and 2. Here's our negative 1 and our negative 2. Here's our negative 1 on the y and our negative 2 on the y. There's 0, 0. There's 1, 2. Ignore that. I'll be honest, I'm just kind of playing around with it now. 2, 4. Where is 4? Maybe it's like right there. Negative 1, negative 2. Negative 2, negative 4, maybe down here. And you can see it's the same idea. I'm just not explicitly telling you where these points are. And if we're really lucky, maybe we can connect these. Wow, this is a bad line, guys. But theoretically, we can connect them with a line. There's another way that we can write this function. This is sometimes referred to as functional notation, where we again have our outputs as some function of the input. And so this specific one, I believe, is 2 times x. So whatever you give me as an input, my function just doubles it. So you plug in x is 0. So, sorry, this actually should be h. So we have h of 0 is 2 times 0, which is 0. We have input 0, we have output 0. We have h of negative 2 is 2 times negative 2, giving us negative 4. All well and good. Everything that we expected back from college algebra. Hopefully that's not new enough to be interesting. Okay. Now, let's say I didn't tell you the rule, but I did tell you the graph. So for example, here's a somewhat interesting picture that I could draw. The question is it a function? Well, you don't really have access to its inputs and outputs. So the question is, how does it repeat? Or sorry, how do we see that specific repetition that tells me you are not a function? And the answer is, and I'm actually going to try to build something here. So as we go along in this, as we go a little bit further, maybe I'll get better at this kind of writing. Wow, that's way too thick. Let's go calligraphy brush. Okay. So I'm just going to make the vertical line. And this is actually something sometimes referred to as the vertical line test. Let's go back to just the brush. Actually, I think what we had before was the pencil. So there's something called the vertical line test, which is, this is where I'm going to get real fancy with it, guys. We pass this vertical line through the function. We ask ourselves, where is it touching this function? And as long as it only touches this function one time, we have the ability to say it passes the vertical line test. This is a function. So, what about some non-functions, or maybe some different functions? We'll get rid of this one. Can we come up maybe with a different function? Something that is going to be not a function. It's not going to pass the vertical line test. Here's a function. Once again, we ask ourselves, is it possible for me to do what I want to do? If we pass this vertical line, oh, it seems good, seems good. Oh, right here, our vertical line is touching the graph at multiple places. You should really think about this as a thicker line. So as you can see, as it starts to touch this line multiple times, I don't even need to know the underlying rule. I can tell you most assuredly, this function right here, not a function. And that's really a horrible sentence to say. What I really mean is that the relationship you're describing graphically right here is not a function. We won't spend too much on things that are not functions. Most of what we're interested in are actual functions. Now, another thing that we can kind of talk about when it comes to functions is we can talk about, there's something called, there are even functions and there are odd functions. And you can kind of think of the prototypical even function as f of x and the prototypical even and odd functions as even and odd powers of x. So for even, we're going to go x squared, and for odd, we're going to go just x. And there's an important relationship. Notice on an even function like what I've given you. And in fact, once again, this is a time where hopefully I can get better at using this online whiteboard. We'll call this one F, we'll call this one G. So, f of negative x. What happens when you plug in a negative into this equation? Well, that's going to be negative x squared, which is negative x times negative x, which turns out to be x squared, which is the original f of x. Even functions have the property that as you plug in the negative of any number, it's the same as the positive. Versus odd functions is going to be negative x, which I can write as negative times x, which is, of course, negative g of x. Odd functions are different. I plugged in a negative x, and I get the negative gets pulled outside. Whereas an even function, the negative just disappears. On an odd function, the negative gets pulled out. This also has a nice visual description. So here's an example of an even function, x squared. And notice it has this nice symmetry about this vertical axis. Now, you might expect the odd function to have a symmetry about the horizontal axis, but no, it actually is this nice symmetry about this sort of 45-degree angled axis. That's where the symmetry is starting to be. So, how do you determine if a function is odd or even? Well, you just plug in the negative and you try to see. So, what if we took a look at a function h that was, for example, let's take a look at x minus 3 to the 4th plus 9. H of negative x is going to be negative x minus 3 to the 4 plus 9, which is, of course, multiplying it out, it's going to be x to the 4th plus 3x cubed minus 9x squared plus 27x minus, or plus, I'll be honest, I picked a bad one to start. And this is something that happens a lot. Oh no, I don't want to keep multiplying this out and then subtracting the 9. So, what else can we use? Well, we do have something that we could use that hopefully I had a little bit prepared, which is that if we use something like a graphing calculator, and I'll be using the Desmos graphing calculator, if we type in what we just said, x minus 3 power 4 minus 9. The question is, it doesn't have this axis of symmetry. Is f of 1 equal to f of negative 1? And clearly, those two heights are different. Here's f of 1. We get something around 7. We don't get 7 for f of negative 1. If we zoomed out, we could probably find out where it is. But all we know is that it breaks it one place, it's going to break it every place. So we actually know h, even though the power is even, I want to point out, it is not even or odd. It doesn't have that specific property. Okay? Most of our functions are not even or odd. But it's important to know when something is even or odd, because there's some tips or tricks that we can make that might speed up some of our calculations. And that's just something that we'll kind of hint at as we go forward. It's very important to just put for the record, sine of x is an odd function, and cosine of x is an even function. And these are some trigonometric functions that we will talk about further on in this chapter. But as we start to define our even and oddness, I just want to state for the record that specifically sine is an odd function and cosine is an even function because it has these specific properties. Sine of negative x turns out to be negative sine of x. Cosine of negative x turns out to be cosine of positive x. Okay? Now, time to, as a final thing that I want to talk about in this video, is I just want to talk about what most of this class kind of boils down to. Something that you're going to experience quite a bit in this class, in the actual act of moving things around. So let's call f of x, let's define the function x squared plus 1. And so we want to be able to plug in, let's say, f of 3, in which case we're going to make sure to work it out as best we can, following all the rules, all the right things that we should be placing at every attempt. But we might run into something that maybe some of you are not as comfortable with. Like, what is f of h? Well, the rule is, going back to the inputs and outputs, x is our input, and f of x is our output. So whenever we plug into f, what does it do? It takes our input x, it squares x, and it adds 1. So when our input changes to h, we're going to square h and add 1. Okay. What about something like this? Whoa. I'd like that back, please. What about something like f of x plus h? Well, what do? We take x plus h, we square it, and we add 1. Now, very, very important. What is x plus h squared? It is not x squared plus h squared. Okay? If you want to really think about what x plus h squared is, it's x plus h times x plus h, multiplying all of the pairs that we can make, we get x squared plus xh plus hx plus h squared. And specifically, those two things are the same thing. X squared plus 2xh plus h squared. That's what we get. X squared plus 2xh plus h squared. And then we add our 1. Can we do anything with this? No. That is as far as we can go. Very, very important that you actually be sitting down, writing something out. It can be digital, but it's very important that you start to manipulate these things out, because the way that I'm going to teach you calculus requires that you place these things down and you utilize them and you make sure that everything we have goes correctly. So that's all it for this video. Hopefully, if you're new to the course, hopefully you've introduced yourself. Make sure you take that hardware check test. I just want to make sure that we're not going to have any problems as we go forward. And of course, if you ever need me, you know where to find me. My email, tchisholm1@uca.edu, and I'd be happy to hopefully answer your question. Have a wonderful rest of your days, and I'll see you in the next